So we are dealing with the 10th problem in the collision mechanics series, and the 10th problem in the collision mechanics series is problem number 1.175, and this is perhaps the last problem of the collision mechanics series which we are solving, and it is a very interesting problem. The problem is stating a particle of mass m1 collides elastically with a stationary particle of mass m2 where m1 is greater than m2. Find the maximum angle through which the striking particle may deviate as a result of the collision. So the collision is elastic in nature, and let us first of all draw the situation which is described diagrammatically. So this is the situation which is described in the problem, that a particle of mass m1 strikes the mass m2 and collides elastically, and then after the collision we are considering that m1 is going at an angle theta with the initial direction of motion, and m2 is moving with a angle theta naught with the initial direction of motion, and we need to calculate the maximum value of theta, that is the maximum angle through which the striking particle may deviate. So we need to maximize theta in this particular problem. Now we begin with the momentum conservation statement, and we will be conserving momentum along x-axis. So P initial in the x direction is equal to P final in the x direction, and hence we express the equation where we write momentum P is equal to m1 times u, momentum P1 as m1 v1, and P2 as m2 v2, and these are all vectorially written. So over here if we consider along x-axis, so the velocity u is along x-axis, and hence the expression that we have is going to be p, that is m1 into u, and this is equal to. So now if we write in the x direction, so we can break the component p1 along x-axis, that is it will become p1 cos theta, and this one will become p2 cos theta naught. So we will get something like this. Now obviously it can come to mind that why exactly in all the previous problems which we have discussed we never write the equation in terms of momentum, or maybe we have written once in the maybe in the 8th problem we have done that of the series. So why exactly we are doing this? Because the question is not providing us any data about the initial velocity, the final velocities. So we are trying to keep the variable at low, and we will also try to write kinetic energy in terms of momentum so that we can focus only on the variable which is to be discussed, that is theta. So that is the sole purpose why we are focusing only on the momentum aspect of the problem. And we have a equation like this. So if we write cos theta naught, then we can rewrite this expression as p minus p1 cos theta is equal to p2 cos theta naught, and if we square this expression, so then we have p minus p1 cos theta, and then we square this term, so we get p2 square cos square theta naught. Now similarly, if we think in terms of initial momentum in the y direction and we equate it with the final momentum in the y direction, then we can say that initially there is no momentum in the y direction, that is the initial momentum in the y direction is absent or zero. And then over here if we write the momentum in the y direction, then it is plus m1 v1 sine theta, and then minus m2 v2 sine theta naught. So if we write in terms of theta naught, then we can write it in terms of momentum. So we will write it as p1 sine theta naught, and then it is p2 sine theta naught. So therefore we can write over here as p1 square sine square theta as p2 square sine square theta naught. So we'll have a equation like this. So we are referring this one as equation 1 and this one as equation 2 for this particular problem. And now if we eliminate theta naught, because theta naught is nowhere to be discussed in the problem, so we can add the two expressions, and that is the reason why we have expressed sine square theta and cos square theta term, so that on adding it will eliminate theta naught, and we will get the equation of the form that p square or p1 square plus p square minus 2p p1 cos theta equals p2 square. So simply we add the two equations, we open this bracket up and we get this form. So we will be referring this expression as equation 3. And now the next thing that we apply is kinetic energy conservation. So kinetic energy is also conserved. So we write kinetic energy initial or before collision is equal to kinetic energy final, and hence if we write the expression, so the initial kinetic energy is equal to p square by 2 m1, and it is equal to p1 square by 2 m1 plus p2 square by 2 m2. Now if we put the value of p1 square from equation 3, so then the equation 4 will modify itself, and the modified equation is going to take a form like this. So it will take the form p square by 2 m1 is equal to p1 square by 2 m1 plus p1 square by 2 m2 plus p square by 2 m2 minus 2p p1 cos theta by 2 m2. So we will get this equation of this form, and now it is a quadratic equation in terms of p1 square. So if we write this or arrange the variable in terms of quadratic equation for p1 square, then we rewrite this expression to have the form half of 1 by m1 plus 1 by m2 p1 square minus 2p cos theta by 2 m2, or we can just remove this 2 p1 plus p square by 2 m2 minus p square by 2 m1, and this is equal to 0. So we have this equation of this form where we have we can refer this one as A, we will be referring this part as B and this part as C, and now we can say that we are looking for theta. It is very important for us to understand that we are looking for theta, and at this point we need to have a thought. So the thought is, the problem is not asking us to solve for p1 but the problem is asking us to calculate the value for theta, and the question is asking us to calculate the maximum angle through which the striking particle may deviate as a result of the collision. And hence over here, instead of solving for p1, we are going to look for the discriminant of this quadratic equation, and since it must have the real root possible, so over here we write that if we think in terms of discriminant of this quadratic equation, and we say that the discriminant is greater than or equal to 0 because the roots are real or equal, so we can do b square minus 4ac greater than or equal to 0, and over here if we do that, then we can say b square, that is p square cos square theta by m2 square. So b square minus 4 ac, so 4 m2 plus m1 by m1 m2 p square by 2 1 by m2 minus 1 by m1, so we write it as m1 minus m2 upon m1 m2, and this is greater than equal to 0. So we are going to have this expression, and then if we remove the p square part because it is greater than equal to 0, and since this expression is in terms of cos theta and we are looking for the maximum angle, so the value of theta will be maximum around 0. So we can say that if we equate this expression to 0, then we will get the maximum possible value for cos theta, and hence we can solve it as cos square theta by m2 square is equal to m1 square minus m2 square by m1 square m2 square, and then if we remove this m2 square, then we will get the answer over here as cos square theta equals m1 square minus m2 square by m1 square. So now the answer is provided to us in terms of sine theta, and if we write it in terms of sine theta, that cos square theta is looking like this. So this part is hypotenuse, this must be the base, or we can do 1 minus sine square theta. So sine square theta or sine theta max, so therefore we are writing sine theta max, so this is equal to m2 by m1, and this value that we obtain m2 by m1 is going to have a possible answer only if the value m1 is greater than m2, and hence this fact is also stated in the problem that the stationary particle m2 and then m1 is greater than m2. So this result that we have obtained is applicable only when m1 is greater than m2. So this is how we are going to approach this problem, and this is the final solution for this problem which we have discussed, problem number 1.175.